Welcome back, folks. So as promised, we're going to take a look at two rational functions here, and depending on the length of the video, we might have to split this one up into two shorter videos. But our goal here is to just sketch what these graphs look like. Okay, so the first one here on the left is g of x is equal to 1 over x minus 3. Okay, so first thing that I'm going to do is, once again, find that vertical asymptote. So if you look back at the last video, a vertical asymptote, and I'll kind of find that here, our vertical asymptote, I'll just abbreviate that as VA, occurs when, or I'll say where, you get an example of the function looking like a number, usually 1, over 0, right? Because meaning that you can't actually plug that point in. Where does that happen in this function? Well, you can kind of see that in the denominator, we have x minus 3, and so the value of x that makes that happen is 3. So our vertical asymptote is going to happen at x equals 3. And so I'll draw a rough sketch here. Oops. And so here's, I'm going to say 3 is right there. And so we know we cannot plug in x equals 3. Right? So by the way, we'll just say that here. Our domain for this one is that x cannot equal 3. The range, we notice, again, this is very similar to the parent function 1 over x, where no matter how big or how small x is, 1 divided by that number is never actually going to be 0. And so we can see here that our output is that g of x is never going to equal 0. Or you could say y is never equal to 0. That's fine too. And so that's going to tell us that we actually have another horizontal asymptote right there. I'll draw that in green. And now you can see, well, we can kind of see what's going to happen if I plug in a number like 3.1, a number that's on the left side, sorry, let's say the right side of 3. Well, as it gets bigger and bigger and bigger, your output is going to get smaller and smaller and smaller. However, so that's going to be something like that. It's going to look something like that. But as you get closer to 3 and ever so slightly here, so for example, g of 3.1, pretend, you're going to have 1 over 3.1 minus 3, which is 1 over 0.1, which is actually 10. So it's actually going to be way up here. And so you can see, as you get closer to 3, just like we saw in the, the parent function in the last video, 1 over x, as you get closer to that vertical asymptote, you're shooting up, right? If we think about something on the opposite side, so for example, maybe g of 2.9, we're going to get 1 over 2.9 minus 3.9, which is 1 over negative 0.1. That's going to be negative 10. And we can see there, hey, we're really close to 3, but on the left side now, so we're negative. So as we get closer to 3 from this side, we're going negative. And as expected also, if we plug in a really, really big negative number, like negative 10,000, we're going to get really, really small and close to 0, like that. So this is what that graph looks like. Notice, this graph actually looks exactly the same as 1 over x. It's just been kind of pushed over 3 units. All right? Okay, so the question is, what about this slightly more interesting graph over here? Well, let's take a look at that. Okay, so one thing that jumps out, and I would totally not blame you for this, is that, oh, wait a minute. Can't I just cancel out the x plus 2 and the x plus 2? Huh, well, let's do that, right? So we're going to cancel those out, like so, and we're going to end up with 1 over x minus 3. Oh, sorry, you can't see that, but notice that's the exact same graph that we just did, right? So I'm going to draw this one in, I guess, blue here, right? So check this out. We're at 3 right here. So there's our vertical asymptote. Likewise, we'll have a horizontal one right there. And we're going to look something like that. Okay. Here's the funky thing. this is actually almost true. So let's try plugging in some values. Okay, so I'm going to evaluate, say, h of, and I realize my head's in the way. Let's scooch over here. Let's plug in h of 1. And I'm going to plug this into the original function before we cancel out the x plus 2's. Okay, so that would be, let's see, 1 plus 2, which is 3 on top, and the bottom will have 3. And then 1 minus 3 will be negative 2. Oh, wait a minute. Okay, so I see that we can actually just cross off the 3 and 3, and we'll get negative 1/2. Okay, well, that's not so bad. If I plug in h of, let's say, 0 now, I'll get 2 over 2 times negative 3. And once again, I can cross off the 2's. Seems pretty straightforward. Check this out, though. What if I plug in negative 2? H of negative 2. Oh, sorry. I left one thing out. We notice here that this then would be the exact same thing as g of negative 2. Sorry, g of 1. And this would also be the same thing as saying g of 0. So h of 1, g of 1, same value. H of 0, g of 0, same value. But let's compare h of negative 2 and g of negative 2. So h of negative 2 is going to be equal to, let's see, well, negative 2 plus 2 would be like so. I'm actually going to write this one all out. And likewise for g of negative 2 would equal, let's see, 1 over negative 2 minus 3. For g of negative 2 is going to equal 1/5, negative 1/5. But h is a little bit more complicated because we're going to get 0 over 0 times negative 5. Can I just cancel out the 0 and 0? Unfortunately not, because what you would then be saying is that you would be saying that 0 over 0 is actually equal to 1, which is not quite something we want to say. It's a little bit more complicated than I want to get into, at least for now, but we don't want to be able to say that. And so actually what's going on is that h of negative 2 is actually not defined and should actually have no solution and no value. Right there. But g of negative 2 does have a value. It's negative 1/5. So what happens? What's the deal here? Well, it turns out that it all comes back to this idea of what we cancel out, the x plus 2's. This is actually true almost all the time. Excuse me. So it is fair to cross off the x plus 2 and then say that h of x is equal to this function if, big if, x is not equal to 2. Negative 2, excuse me. If x is not equal to negative 2. Okay. Why? Well, because if we plug in negative 2, then we actually can't cross off those two factors, those two terms. Okay? So it turns out the domain actually of h, which I'll do in red here, the domain of h of x is all real numbers except 3, because we can't plug in 3 because we'll divide by 0. Cannot equal 3. But also we can't equal 2, negative 2, because we don't want that 0 over 0 either. Okay. But notice, if we were to plug in points on either side of negative 2, close to negative 2, it's not going to shoot up and make this weird drastic change like the original function does on around x equals 3. And why is that? Well, again, as long as x is not exactly equal to negative 2, h and g are exactly the same. The only problem happens when, again, you plug in negative 2 for h. So what does this mean about the graph? Well, it turns out then that these two graphs, h and g, are exactly the same except at that one point of concern. So h, which I'm going to draw in red here, is exactly the same. Almost. The only thing that we need to do is erase this point. 2 comma negative 1/5. Because again, you can't have that point in graph H. So let's see, this point right here, I'll just estimate it here. Let's say that's at -2. And the way we draw that is we draw a little hole and just kind of erase it there. That point is -2 comma negative 1/5 and has been omitted or removed from the graph. So this red graph with the little hole in it is the graph of h of x. This point that we've plucked out, that has a special name. It's called a removable discontinuity. Removable discontinuity. Why is it called a discontinuity? Well, it's a discontinuity because it makes your graph not continuous. There's a break in the graph or a hole in the graph. Right? A vertical asymptote, by the way, is also a type of discontinuity because it breaks the graph into another piece. We call it removable because we essentially removed it by canceling out dx plus 2's. So that's why it's called removable discontinuity. Basically means that it's a hole in the graph. Okay. Whew. In summary, you're going to find the removable discontinuities by the term that gets canceled out. And you're going to find a vertical asymptote by the x value that causes you to divide by 0. Not 0 over 0, but constant on top over 0. In the next next video, we'll talk about this very clearly, hopefully. Okay, but hopefully this gave you an idea of how to find and how to graph discontinuities on a rational function, and just how to graph a rational function and how to find their discontinuities. Okay, thanks for watching. Stay spicy, folks.